is simply the number of forces acting on the object. Yeah, so how many forces are acting on the object or trying to pull this object in the opposite directions? So we are having two forces. There's friction and there is the 100 newtons that is trying to make this guy move in this direction, this side. So if we're having these two opposing forces, we have to find out the force that is going to win, and it's obvious here the 100 will win. The frictional force is happening in the opposite, and friction always loses work. The second law, we said the force is equal to mass and acceleration. So the force that is causing this guy to move is equal to, so we'll say force is equal to this force here, the net force. We're saying the net force will be the 100 newtons, then minus the 19. Then you get your what? You get your resulting force. It's like the thing you used to do in high school, guys. If I give you to say there's 100 pulling this side and there's 19 pulling this side, what will be the force, the overall force? You just do 100 minus 19, because the part that is going to win is this part, right? So you do this minus that. Now, this question here, they were not even asking us to use the second law, because they were just asking for the mu k, the coefficient of friction. And if you are looking for the coefficient of friction, the only equation that you were supposed to use here, Joseph, is that mu k is equal to the normal force. They gave you the mass. The mass here is given to be 50 kg. How do we get the normal force? We said the weight, mg, is always equal to the normal force, because these are always going to be opposing each other in opposite directions. The main reason why the box is able to move in the horizontal line is because the y forces are equal and they're balanced. So it's not jumping up and down. So normal force will be equal to the weight, and the weight here is supposed to be equal to mg. So the mass is 50 kilograms, then times 9.8. So here you get your what? You get your normal force. So let me just use 10, g to be 10, the normal one, the rounded off one. So this will be 500 newtons. That will be our weight. And if this is our normal force, which is our weight, we know that friction was 19. We're looking for mu k, then the normal force is a 500. So meaning you are just supposed to divide both sides by the weight, and you get your mu k. So everything else I gave you was just a distraction. The acceleration and the 100 newtons, those were just distractions. The only equation that has mu k that you are looking for is the formula for friction, which is this guy. So no wonder we're using it. And the mu k here will be, you can punch your 19 over your 500. Then you get your answer. Have you seen what we've done here, Joseph? So the rest of the information was just there to distract you. The only formula that has friction, that has a coefficient of friction, is the mu k. Yeah, so Madam Esther, this will be a bit confusing, but it's okay. Just stay in the meeting. You'll make more sense out of this after you watch the video that I've sent you. Yeah, Macnon, you have a question?
Yes, sir, about the question.
Yes.
So on the first part there, so meaning you only get the friction, right? The friction force, that's how you put on the force.
Yes, you just get the frictional force, yes.
Okay, sir.
Yeah, because the only equation connecting mu k to anything else is just this. Peri che mu k, pe munga ipeze che coefficient of friction yet circle. Ni pamena apache pa equation. So the rest were not necessary. So this is just what you use. Yeah, then the second question I gave was something that looks like this. I gave you a table, a box, and the angle 20 degrees was given, and we were pulling this using 100 newtons. Then I was asking for frictional force and acceleration when mu k, the data given is that mu k is 0.05 and the mass was 20 kilograms. So the question was asking us to get the frictional force, and the second one was to get the acceleration when we are done. So we said the only forces that are acting on this particular guy, the only forces that we're going to be having is simply the x component of the force, the 100 newtons. That's what we're simply going to have. So you need to identify all the forces acting on the object, and in this case, the only forces that we're going to have is 100 cos 20 in the x. There's the x component of the force, then there is a y component of the force, which is 100 sine what? Sine 20. So I will erase this guy here. So this now, I will erase this. We have resolved this. The same thing you used to do on vectors. Then aside from this, you know to say the box has weight, right? Weight is equal to mg. Then there is a normal force here. Then we know to say there is friction also this side. So this is the first step per Newton's laws. The hardest part when you're doing Newton's laws is to see all the forces acting on that particular object. And for this question that I gave you, these are the forces acting on the object. So we just resolved the force that was given because we are given the r and the theta. So according to your vectors, whenever you have the resultant and the direction, you can always resolve it into the x and y component. So that's what we basically did. So after we've done that, we are now having forces in the x-axis, which are the ones that are only responsible for motion, because this thing is moving, right? It's moving in this direction. So the forces that are responsible here, will make equations before we even discuss how to get the frictional force and the acceleration. Tizapanga my equation. So we'll say the winning force, which is 100 cos 20, 100 cos 20, minus the losing force, which is frictional. Our frictional force is simply equal to ma. This is the first equation we make in the x, so we need to write this. This is the first equation. This is what we always do. Winning forces minus losing forces is equal to ma. That's the reason why we call this guy to be F net, because it's the net force. Yeah, so this is what we have. And the equations in the y that we're going to make, the equations in the y that we're simply going to make is that we're having the normal force here. We have the normal force. There is a force that the ground is pushing on the box above. Then there's a y component here. Then there's this. So we say the forces acting up are equal to the forces acting down. These two should be equal to the weight. That's the reason why this thing is stable and it's not jumping up and down. Yeah, so we're just saying normal force plus 100, then sine 20 is equal to mg, which is the weight, meaning our normal force is just mg minus the 100, then sine what? Sine 20. So if this was to be given, this is 20, 20 by, I'll use g, I'll use 10, then minus your 100 sine 20. So here you can punch this, you get your normal force. This is 200 minus your 100 sine 20. So you can just punch this here, you can get your normal force. So what do you get as your normal force? Anyone who can just punch this, anyone sitting next to a calculator.
One 65.8.
165.8. Then
Yes.
This is in terms of y, the y forces. So because it's static, in the y, it's not jumping up and down. No wonder we're saying these forces are balanced. That's what we mean here. No wonder we're not subtracting. We're just saying these two, the normal force, the force with which the ground is pushing up the box, and the y component of the force we resolved, these two added together are equal to the weight. That's why it's not moving. So this is the 165.8 that you're getting. And the forces in the x are not balanced. That's the reason why this thing is actually moving. And the winning force, 100 cos 20, minus the force that is slowing us down, which is the friction, will always give us ma. This is the first equation we wrote in x. Now that we know what the normal force is, we now make our third equation. So the third equation, we said friction is always equal to the coefficient of friction multiplying the normal force. So the coefficient of friction was given in the question, and it was 0.05, this guy here. So we're just going to use it to get the friction. So this is 0.05, and we multiply it by 165.8 newtons. So just multiply the answer you've gotten by 0.05. What do you get?
You mean 8.29.
So the friction is 8.29 newtons. So we know to say this guy is the amount of force that we're being slowed with. So it's slowing down by 8 point that. So we're going to say the winning force was 100 cos 20. Then this guy is, okay, so this already answers your part A of the question. You found your friction. And we're going to say the winning force, now we know what friction is. It's 8.29. We put it there, is equal to the mass. The mass times acceleration. So the mass was given in the question. The mass was what? The mass was 20 kilograms, if I'm not mistaken. We're looking for acceleration. So here we'll just divide by 20. Also this side will divide by 20. Yeah, so this is kilograms. So meaning your acceleration will just be the 100 cos 20 minus the frictional force, then 29, everything over a 20. What do you get? So what do you get for this part if you punch it? 4.28. So 4.28 meters per second squared. So this is simply your acceleration. Yeah, so this is how you were supposed to answer that question, Joseph, the one that I gave you. Yeah, so this is the most important part of Newton's laws, is identifying all the forces. So this is basically what we have. So if this is okay, guys, I would like to dwell now on what I intended us to do today. So it may be a bit challenging at first to see all this, but with time, with more practice, the only remedy for physics is more practice. The more you do questions, the more you get familiar with how to do things. So under applications, we are simply going to look at 3 cases. So the first case that we're going to look at is when you're dealing with a coupled objects. Yeah, so coupled objects. Yeah, so coupled objects. So I'm sending the question in the group. It's from your tutorial sheet. Yeah, so I didn't manage to transfer it from the phone to the laptop. So I'd rather just send a screenshot so that I don't waste time writing it again. So I'll just say example. So this is question 4 from the Physics 1010 tutorial sheet that I've just forwarded. So whenever you're dealing with coupled objects, you can either treat it as one thing. So here they are simply saying there is the first mass, which is M1, and then there's a bigger mass here, which is going to be called M2. So I'll give you the general way of dealing with this before I even answer the question, so that you know how to formulate the formulas, how to come up with the formulas. So this is what we are having. This is on a surface. So the way you treat this is the same way you're going to treat something that looks like this if they are coupled together, but there's a difference in terms of there's a string in between them. It's like this is mass 1 and this is mass 2. How you treat this is the same way you treat this, because they are all attached, they are linked. So first and foremost, there is a force that is causing these guys to move, and we're going to take the best case scenario that this thing is moving in front. So there's always some tension or a force that is responsible for this to move in front. So let's call it F. Then in between, whether this case or this case, in between there is tension. If a car is towing another car, and this is, let's say, the metal that we're using to tow this first car. This is let's call it car 2. This is car 1. So there is tension in the metal that we're using to tow the second car. The same applies even if we don't put any tension in between. We're just saying the mass A, the M1 object is pushing against the surface of mass 2, and that same push is equivalent to this tension that we are having in between here. Yeah, so even if they've put it to be closed like this, you can split it per cut and then let it be like this. So now if there is no friction, so I'll give you case 1 where there is no friction. If there is no friction and your object is given like this, you are going to make two equations. So with respect to the first car, this car here that you are seeing here, the car 1, M2, the force that is acting on M2 is this force here. This is F. So it's like we cut it on the middle, and if we cut it, or rather split it, we're going to have the M1. The only force acting on M1 is the tension, which is pushing it in this direction because we are pulling it. Then on the M2, there were two forces acting on it, because remember, for every action, there's an equal but opposite reaction. So for the tension that we are having between M1 and M2, with respect to M1, it's a forward force. It's pulling M1 in front. But with respect to M2, it's slowing it down, right? So if you are pulling someone, with respect to that person is being helped, right? But with respect to you, you are being slowed down. So no wonder we are saying this T with respect to M2 will be facing in the opposite direction. Then the force is directly linked to M2. So this is the only force that is causing M2 to move. So meaning, this is a case where there's no friction. Taijuba Packard, these guys were attached, they were coupled. So we've split them on the middle, and now we're going to say the force causing this guy to move is T1, the tension, the mass 1, and the acceleration. That's the first equation. Then for the second object, the winning force is this guy, the losing force is that. So we'll say F minus the tension is equal to M2 and acceleration. These are the only two equations you will have if there is no friction and it's a coupled system. So this will answer our question there on number 4. They are saying two blocks with masses M1 3.2 kilograms and M2 with 4.1 are touching each other on a frictionless table. If the force F is the one that we're using to pull the whole thing in front, like to move. So you can picture F to be the force that is in front. So our example there is from the tutorial sheet. In as much as they've said there is M1 and then there is M2, so there is M1, then there is M2. The force they've put at the back here is the same as the force that we are calling F this side. What is causing this thing to move is F, right? Then we're going to separate these guys into two equal parts. So we're going to separate it into two equal parts. So I'll show you method 1. Method 1, we are separating them. We are saying M1 is moving because it's being pulled by a tension from the M2. And M2 is moving because of the force F that we are pulling it with. And it's also being slowed down by M1 because it's also trying to pull M1. So we're just using the same equations that I'm giving you here on top. I said even if they put it like this, you can split it per kati, then you know to say M2 is pulling M1. So you have to write a tension. There is tension in between these two guys. And tension is a force. So with respect to this first object, tension that we are getting here will just be M1 and acceleration. That's the first equation. And the second one, we have the force. I'll still write the same thing, minus the tension, which is M2 and acceleration. The only connection between these two guys is the T and the acceleration because it's a coupled thing, meaning they're moving together regardless at the same time. So if a car is towing another car, in as much as the other car in front may be having a higher mass, the tension in between the cord joining them is the same. They are feeling the same, just that M2 is feeling this in the opposite because it's using its energy to pull the other guy. This guy is feeling it in the positive, but the acceleration is going to be the same. So if you make your substitutions there, they are saying if they struck, what is the acceleration of the two blocks, and then B, they're saying what does the force M push against M2, that's the tension. Then now they're saying repeat A and B if the force is in the reverse direction, pushing on M2 rather than on M1. So this is going in this direction. No wonder we are taking this. And we can do the replacements here. We're just going to say T is equal to mass 1 was given to be 3.2. Then we put that. That's the first equation. On the second equation, the only thing we know is F, which was 6.8. So we'll say 6.8 minus T. Now we know what T is. T is the same as 3A. This is equal to, the mass 2 is simply 4.1. So it's 4.1 times acceleration. So I've just made replacements. These are the two equations that we are having. There is this, and there is also this equation here. Then from these two equations, you notice we can either solve them simultaneously by bringing this on the other side, or we can just make a substitution. We know what T is. T is 3.2A. So where there is T here, we'll replace with. So 6.8 minus 3.2A is equal to your 4.1A. So that now we'll get 6.8 is equal to 4.1A plus 3.2A. This will be 6.8 is equal to, when we add this, we'll simply get a 7.3A. You can divide by 7.3 and also a 7.3 so that we get our acceleration. Your acceleration will be, by the time you divide this, your acceleration I think should be the one they got here, which is 0.932 meters per second squared. This is your acceleration. Once you get your acceleration, you can replace it in this equation. Then you know the tension, the force with which M1 was pushing against M2, or the force with which M2 was pulling M1. So you can say that in two ways. Yeah, so because the tension with respect to the first object, it's pushing against M2, right? So the tension in between per cut. So M1 is pushing on M2, or rather we can say the force with which M2 is pulling M1. So this will give you an answer, and your tension should be, when you replace, so tension is what? 3.2 times A. You do your 3.2, your A is 0.932. Your tension should give us the answer we're getting there, which is 3.82. Yeah, something like that. So hope this makes sense, guys. But let's analyze it, and then let me take your questions now, because this is one of the challenging topics you start having in physics. When you cross this bridge, everything else becomes easy. Yeah, because here, all the knowledge of vectors and seeing the forces, you have to visualize things. Yeah, so any questions here? Macnon, which part here is confusing, or would you like me to re-explain again? So in a case where there was friction, so in case 2, imagine there was friction. It was still coupled, so the same information, but imagine there was friction, and I'll say mu is equal to 0.01. So I'll use the same information again, but I'll say now the surface is rough, so there is M1 pushing against M2, and we are pulling this by a force of 6.8 newtons. Now, you can do this in two ways. It's either you treat this as if it's one object, because nivogwirana, meaning they are moving with the same acceleration. What you can just do is just write this guy here is what? This guy here is simply what? It's simply the winning force. Then, because there's friction involved, so there should be friction in the opposite direction, right? So there's friction in the opposite direction. And if we treat this to be one object, we'll just add the two masses. So just add the two masses, which 3.2 and 4.1, meaning izankala chemunga ni 3.2 plus 4.1, so just be 7.3 kg. So when we treat it as a single object, even the weight as well, and then the normal force will be the same. So weight is equal to mg, so our mass and our gravity. You know your mass that we are discussing is simply mass 1 plus mass 2. Yeah, so you can do that if you want, but I'll show you the longer way, because a proper way to handle it is to differentiate the fact that the friction that this object will be feeling is not the same as the friction that the second object will be feeling, because the masses are different. Yeah, if you are moving and the car is moving on the same tarmac, the friction you experience is not the same as the friction that the car experiences. The higher the mass, or the more the mass, the more the friction an object feels. So this is simply going to be split into two. So we'll get the mass 1. So the only forces acting on mass 1 is the tension that is trying to pull it, and this is how we're going to say M1, and we know to say M1 has weight, so there's weight, which is M1G, and then we are having normal force. It has its own friction, so we call it FK1. Then the second object, mass 2, only has the 6.8 pulling it this side. There was tension. Remember the case we are from doing when there's no friction. There was tension. Now there's a friction. Let's call this FK2. And this thing here has normal force. And now it has its own weight, which is M2G. So now we'll formulate equations. So there will be 3 equations here and 3 equations here. So the 3 equations you have for the first object is that the normal force will be equal to the mass 1 and the g. That's the first thing you notice. The second thing is that you can always get your frictional force, frictional 1, is equal to the mu k that we're given times this normal force that you are getting. And the last one is that you can always get the tension minus the friction 1 to be responsible for the movement of M1. These are the 3 equations this side. Then this side you have normal force is equal to M2G. Then the second one you have the frictional force 2 is simply equal to the mu k times the M2. This is just the normal force for this. This is N. Then the other one you say your 6.8. The winning force minus the 2 losing forces, which is minus tension minus the frictional force. This gives us M2 and A. The only common thing between these two objects is that they have the same tension. They're experiencing the same tension in between them, and they're having the same acceleration because they are moving at the same time. So you use both equations. So this side you get your normal force. I'll just use 10 as my G. So I'll say the mass, which is 3.2 by 10, that is going to be 32 newtons. Then our mu is 0.01. So 0.01 times 32, that should give us, I think 0.32 if I'm not mistaken. So if you try to multiply this, if you try to multiply your mu, so we're saying FK1 is equal to 0.01, then multiply this with 32 newtons. What do you get? Should be 0.32 if I'm not mistaken. This should be what you are getting. This side, the normal force was what? Let's try doing them at the same time. Normal force will be the 4.1 by 10. I'm using G as 10. This will just be 41 newtons, meaning our FK2 is equal to 0.01 times 41. This will be 0.41 newtons. So I hope this is what you're getting on your calculators. Now we know that tension, our tension minus the friction, 0.32, is equal to the first mass, 3.2, then A. This side, you're having 6.8 minus the tension, minus the frictional force, which is 0.41, then is equal to the mass, which is 4.1A. So you know to say tension is equal to, from this side, you can make T to be the subject, which is just 0.32. So we get this and replace it wherever there is tension here. So we're now going to have 6.8 minus these two guys. There is 3.2A and minus 0.32. Then minus 0.41 is equal to 4.1A. Then here we simply solve for 6.8 minus 3.2A plus 0.32, then minus 0.41 is equal to 4.1A. So 6.8 minus this guy here, so 6.8, 0.32, this will simply be 8, that will be 7. Yeah, so this is going to be 6.7. Then minus, we're adding here, it's 6.8 plus 0.32, this will be a 2, 8, 9, 10, 11, that's 11, this will be 7 point that, so meaning I can just put my 7.12. So for those with a calculator, I just want you to confirm this, then minus 0.41, so this is a 2, so this will be a 2, that's going to be, we borrow 1 there, that's going to be 11. 11 minus 4, that's going to be a 7, so this is 6.72, so 6.72 minus 3.2A is equal to 4.1A. Then here we just have 6.72. Take this on the other side, it will give you 7.3A. Then we divide both sides by this. So you'll notice that with friction, your acceleration has... yes?
Supposed to be 6.71.
6.71, yes, 2 minus 1, yeah, so 6.71, yeah, so this is going to be 6.71. So if you divide by a 7.3, what do we get? Okay, 0.92 meters per second square, that's your acceleration. Now you have your acceleration, you can just use it back in this equation to find the what? To find the tension, because we say tension was equal to this. Yeah, so you can just use this equation, put the acceleration there, then you get your tension. So you'll notice that the acceleration has reduced when there's friction involved. Initially, we got our acceleration to be, when there was no friction, you notice our acceleration was what? It was something like, what did we get here? I think we got, here was 0.932, 0.932. Then here, what are we getting? Okay, yeah, the difference is minor, but it's still significant. The reason being, our coefficient of friction was very less. This is when friction is involved. Without friction, it was 0.93. So you notice the difference too. Yeah, so we got this 9.3, then this is 9.2. It's minimal, but you notice that this is greater. So without friction, the objects are going to move at a faster rate, but with friction, they reduce a bit. The reason why the acceleration is minimal, or the difference is minimal, is because of the coefficient of the surface. So the surface was almost smooth. Yeah, there was only something that was negligible. The friction is almost negligible. So This, Macnon, you're saying?
No.
Yeah. So we end here for today.